How is everyone today? Very good? Okay. So, how about yesterday? Everyone enjoy a little bit about program and how it works? I hope you have a bit of time later in tutorial section and you're gonna play a little bit about that, okay? However, if you have any question, just bring it up today and we can discuss. Particularly for today, we have to use that directly to our design. So in these lectures, I will talk a little bit about direct strand. I did it already yesterday, but now in the context that we're doing example. And then I'm gonna go thoroughly about the 3 examples where very typical, right, for member-based design for compression, bending, and shear. Right, and then from that you can follow all the steps. And at the end of the day is we're gonna see how much is simpler, as you can compare with what we did in the 3rd lectures on effective width. And in the other way is better way is it can solve the complex problem. So that's the beauty of direct strength method. Okay, so this is what we're gonna do. Bit of review of direct strength method, and then I go thoroughly on each example of the section that we do here. Okay, so when we talk about direct strength method, so in general, what it is, so it's actually one step a little bit further than effective width. So effective width, that's fine. Professor Winter try different way, or uncommon, just try different way to account for post-buckling. And that's why he just treat a section as the element with just a very effective width, not full width. So that is the way that we work around the problem, but not understanding, importantly, the behavior. So I'm talking about behavior is we understand how it's buckle, how it fail, and failure mode is important. So in DSM, we start from those failure mode that really happen or occur in steel structure, particularly with cold form steel, where you have common open section. We did a couple of examples last couple of lectures. General section, one of the very common section that we use for cold form steel, and of course that is the open section. Then is really sensitive to different failure mode, where it's buckled in local buckling or in distortional buckling. That is something new. And this is flextorsional buckling. That is traditional failure mode of member capacity that we all learn from, not just cold form steel or any other type of structure stability. All right, so DSM, looking at, not DSM, in general, because of the section is thin, then it's easy to buckle in section capacity. All right, so because when you use hot rolled steel, for example, I-beam, U-beam, universal beam from company, right? When they make it, normally they already optimize the section already. So the section somehow is already almost compact. You take all the advantage of every single piece of steel there getting to you. You don't want to waste the capacity of the section, right? You don't want it buckle before it yield. So that is now, in the practice, the company or any manufacturer, they want to maximize. So with hot roll, you hardly, or you can, but the section is quite compact and optimized. However, with thin wall, of course, because the nature of the thinness of the section, then you have to accept that and move on. So it's going to buckle somehow. And then, of course, and the other that we learned before because of high strength steel. The way that the BlueScope or the other company, they make the coin is a high strength steel, G450, G550, then it push up the strength up to 500 megapascal for yield stress. But with that one, in the negative size, getting strong, thinner, stronger, but it doesn't help for buckling. That's why it, of course, is buckle before it yield. So the engineer and the manufacturer, they have to balance how we're going to do it. So they, nothing to do with yield stress, right? It's 550. So we can do a little bit in this time. This one, where we can increase buckling capacity somehow. And then when, in order to do that, as we learn from thin walls, you make the section a little bit more complex, give you a bit of strength in terms of buckling. All right, so that is how we deal with the local buckling or distortional buckling, and that is all about sectional capacity, nothing to do with the strength, the length. Right, so the longer the beam or the shorter beam, it doesn't matter because it's already fully lateral restraint. And if you don't put enough lateral restraint, of course, it's going to buckle in fractional buckling. That's member capacity, so nothing to do with section capacity. Okay, so that is the three distinct or three basic failure mode that in our indirect strength method we can isolate it. We can understand that. So then at the end, what you do, very simple, you just choose the less, and that will govern your design. Okay, so yes?
What about elasticity and plasticity? So sectional bucklings are beyond elasticity and member buckling is within elastic zone? Or?
It can be either. It can land in any zone that you want, depend on the number of rod bridging, depend on the length. You remember in member capacity equation, there's three range. First range is when it is yield. It means that your restraint is good. And the second range, where it takes into account a little bit of inelastic buckling, okay, or non-linear. And then the last one is purely elastic buckling because it's too long, no restraint. When you push a load, it just buckles sideways and twists in fractional torsion. So they all accounted in here. All right. Okay, so we learned from yesterday, and then we're going to do it. So from thin wall, you got a very famous figure that is called signature curve. And now everyone, I hope that clear about halfway length and length. All right. So first minimum point is local buckling. Right, you can see it happened within the element, the junction line still straight. Just buckle in and up and down or in and out in the wave in that element. Right, and then it moves to the second failure mode, which is distortional buckling, where the member subjects to a longer halfway length, and now that halfway length happen at the junction of the lift and the flange. It go up and down in like this one. So that it is distortional buckling. And the third one here is the fundamental elastic buckling of the member. Okay, so in here, this is the beam, so you can see one typical flexural torsional buckling or lateral buckling as we call in US. Okay. Yes, so now, as an engineer, we don't want to design something very good in local buckling, but it's bad in distortional buckling, right? We don't want to design some beam, it's going to fail right here, but it's very thick or good in section capacity. Right. So, for optimization, as an engineer, we need to make sure that those three are very similar. That is the best one. That is the maximum or optimized solution for any type of structure. Okay, so that's good. Now, you can use that using thin wall to the program that I provided to you. Or alternately, you can use CUFSM. It's developed by Professor Ben Schaeffer in Johns Hopkins. So as I mentioned before, they are very similar. Just different interface, depend on how we design. But the engine behind that is all based on finite strip method. The Thingball tool has a little bit more function on that, where I told you yesterday already, where we can solve for shear, we can show for localized loading, and then we can play around with 3D model and then 3D figure. So I think it's another advance of that, but in general, technically, they're all very similar, or you can use both. But anyway, both of them are free. It's up to you how to use that. Okay, so just again, for someone still not sure about that, I'm going to show you. This is halfway length of the local buckling, and this is number of halfway length. So imagine that's yes, 12 halfway length. Each halfway length is about 200 meters or something. So the beam gonna be 2.4 meter or something like that. So this is the halfway length for local buckling, and this is the halfway length for distortional buckling. It's right here, and this is only one halfway length because it's buckled in member capacity. Right, so this is actually, I put in here, this is real length. So the length is equivalent to halfway length when we talk about the member capacity. Okay, so just a review. This is one halfway length. So this is famous figure where the direct strand method equation came from. So this is from the graph from Professor Ben Shepard, and he collected all the testing data around the world. So just on how to calibrate an equation, so as you're aware that it's not just simply we pick up one test series at one places and then we done it and then we propose to the standard. It's not working that way. So in order to get a generic equation, we need to collect the data from everywhere. The more it is, the better. So we can calibrate and get the equation to get a generic equation. And even the other one as well. For example, fastener, screw or bolts. We're not going to choose only one type of bolt made by one particular manufacturer. You have to pick for different type of the spaceman, what we call it, more variety, more generous. So more representative range, so we can calibrate the equation. All right, so this one is famous equation where you can see those equations, the equation that we learned or we got from standard. All right, so this should give you a very simple flow chart, how you use direct strand method for design. Yes?
Last figure.
This one?
From MCR gives the theoretical value, finite strip.
Yep.
And those M test is testing data. So it is not the one-to-one.
M test is all the tests.
Yeah.
Right.
So why this difference is there? Like like initial imperfections, these things are causing the difference between theoretical and test values.
Okay, so I get your point. This is the real test, the actual test that you do. Okay, and this is the curve that we calibrate. Oh, no, we do. Professor Ben Shepard calibrate. So you can see that some area or some test data here probably lie below the curve, because I explained to you before, maybe there's some interaction or some some residual stress or whatever. There's all there. Right. But with the calibration of any design equation, there's two ways to do it. First, you take the mean, as in the US system, or you take a lower bound, as in European equation where they calibrate. So in European, it tends to be a little bit down here because of the conservative. But when you put down here, it means that you have more conservative equation, then you got less 5 factor. But when you fit in the mean as US system how they calibrate it, of course, there is more accurate, not accurate, so it gives you a bit of more load because you put in the mean in the middle. And then you got all the variation in here. And that variation would be taken into account in the 5 factor. So the 5 factor will cover all that, okay? But you remember at the first lecture, when I talk about effective width method, where Von Karman put that is an effective width, and then Winter ship it down. And he shipped a lot more on the lab in here because of the effect of imperfection, residual stress, and all the uncertainty that we don't know. So that's why he put that one down. But when you get to the right in here, when the member getting longer, and you know that the residual stress in cold form steel is not that bad like in hot rolled steel. So that's why you can use probably the same of approaching that curve. Okay? So that is how it works.
There may be some imperfections in the table board sections.
Yep.
Maybe not residual stress, but imperfection may have some effect.
Has some effect. So that's why, you know, at that range is taken into a lot of account. So that's why it dropped a bit, it lied a bit down. Okay. So you can see even the Professor Ben Schaffer proposed that one, but the equation is really based on the theory, all right? So I show you that the 0.4 exponent is local buckling. 1 is Euler, you know, and it's just dropping down depending on the failure mode, but it's just based on the behavior of the elastic buckling equation at the beginning. All right, so this all have some theoretical base behind that. Yes?
How to derive this half-wave length
Yep.
for a particular section? How we can derive half-wave length?
How we can derive half-wave length of?
How we can ascertain this would be the half-wave length for that particular section?
It's the thing will tell you when you run it, and it will go to the minimum point, and that is where the halfway length is. Okay, and the halfway length will be different depending on the cross section or stiffener. If you put a little bit stiffener on, then halfway length may be getting a little bit longer to get a local buckling. Okay, you can play with that with Thin Wood too and see how it works. Okay.
Depends on the plate buckling unit. Aspect ratio of
Yeah, a lot of.
approximately equal to the buckling unit.
Almost local buckling, I can say almost with the plan section. But when you put stiffener in, maybe it's a little bit longer because it's stronger in local buckling in terms of local buckling stiffness. Right, so here just summarize the flowcharts for you for easier use later on. So first is in here, you calculate the elastic buckling, local buckling, and distortional buckling stress or buckling load or load factor. You got that. You got from Thin Wood 2 or CUSSM. All right. So you got those two minimum. You got stress. And then on the other hand in here, from the cross section, you can work it out my. Yield moment, easy, right? You just get Z times with Fy. ZF is a full elastic section modulus of the full section, so easy. You can calculate by hand, or you can calculate using Thin Wood 2. Right. So from that, and then from that, you time with the ZF in here, you got M critical L. So that is the elastic local buckling. Remember here, it's just buckling. All right, M critical L. And then we get a second minimum point, you got M critical distortional buckling. Okay, so that is buckling. And in here, you calculate the lateral buckling. All right, MBE, so that is the member, all right? But that is just from the traditional way to do it. It's not DSM. Everyone can do it from that. And then from that, you can combine and then you can calculate MBE. That is the strength. The elastic, so local buckling. Remember, it's still elastic, local buckling, but now it's strength. It's not buckling. And what I'm talking about strength, because we already cover yielding, imperfection, and it's actually real strength. It's real strength. It's not buckling. Okay. So sometimes it is higher than the real local buckling because of the post buckling. Some range is actually lower than the buckling because of inelastic buckling or the effect of imperfection or whatever. So that curve will cover, will take into account into that. And at the end of the calculation, we got 3 distant number and 3 strengths. And then what we do, we compare together and then we choose the lesser, and then that is the design that you want, or not you want, that govern your design. Yes?
Perception property, for the calculation, you have volume. Can you use F4?
Yes, we add Y. Yep, so it's just U moment when the top fiber and or the bottom fiber get to the U stress, and then that's it. So that's how you done. Now, lip section. I give you very easy example for you to observe and understand that, right? We talk a lot about last couple of lectures. I'm sure that some of you might still confused about LEX and LEYs. And one thing I'm sure that you're still very confused is LEZ. That's a little bit tricky. LEY, LEX, you can understand straight away, but LEZ, you need a bit of understanding about the torsional or warping, but I will explain a little. I try my best, okay? Otherwise, you need to learn a bit about few lectures to understand the warpings and all that, that term, and then you can understand. But now, just bear with me, and I will explain to you. First, that is the wall system, the dry wall system. I'm not sure in India you use the same or not, but it's very popular in Australia. So we build a big frame with open space, and then we divided or we partition room by using dry wall system like this one. We don't build build a big wall, a brick wall or something inside. We use that one. So inside here that is the C section start. What we go is co-form wall start, and then it's go up here up to the height of the building. And on top, we got the rack put on top of that. And the rack will be bolted to the ceiling. Okay, so it's like this one. And the bottom, we only have another rack on the racks on that, so we fit one in. And then in between here, this is knocking. We put the knocking to there's some job for knocking to do, right? It's not just for fun. So what happened? I'm gonna explain to you later. It's gonna hold the C-section in a way. Morning. So firstly, imagine the coordinate axis. All right. So x-axis is the axis about major axis. So major axis is when it bend. So if we see section, and this is normally we donate is the major axis, right? And this is minor axis or asymmetric axis, or normally with C-section, IX is a lot bigger than IY, then we call it strong axis and weak axis. But it's not always correct, right? Because in column, maybe sometimes we have to choose quite wider planche, but maybe similar to the web. So this is particularly for cross section. So in terms of buckling, of course, it will be easier to buckle in y-axis, right? So because in the nature, it will find the weakest way to do. So it's going to go to buckle. So in here, you can see this is ix and iy this way. You can imagine what I'm saying? So when it buckle under compression or compressive load, you can see here, if you put the load on top on the bottom here, then the column by buckle in the red one, okay? So the red one is when the column buckle out of the plane, of that plane. So it means that it buckle this way, isn't it? So it means that it's in x-axis. So that's why we don't have anything to hold that, right? So it means that it's 1/2 wavelength. So that is LOX, LEX. Right, so that will be equivalent to 2,000 meters. That is the real length. However, but when you buckle this way within that, well, what happened? Because of the knocking, it stopped or it divided our column into two halfway. It's actually half. So the way we put the knocking in, that you reduce LEY into half. All right, so that is how we do it. Imagine if you don't have that knocking, LEY now is 2,000. All right, but now we put that knocking in, then you reduce LEY to half. Easy to observe, understand, isn't it? Now, LEZ is a little bit tricky. All right, so I have to use a finite element to model and then to plot for you, and I hope that you can understand it. All right, so this is for LEX and LEY. Now, with LEZ, it really depends on the condition of the boundary condition at the end in here. All right, so imagine now we got that top and bottom, imagine like it welded to our cross section in here at the end. So we don't allow it to move. Another tricky things. So you're gonna ask me, what is move in here? What does it mean? So we stop the cross section at the end here from longitudinal displacement. Ooh, what is that? Longitudinal displacement. All right, I'll explain it later. Okay, just accept that one, and then we'll move to next slide, and then we'll understand what it is. Okay. Now, can you help me? Give me one paper, the sheet of paper. Any spare one? A4. You have any paper? Okay, good. Good. So imagine. So you can do experiment with me. Okay, get one paper. Get one paper out. I will explain to you this term. So it's very important. Get one paper out. Just one paper, right? So imagine we got C-section, so we can sort of fold that somehow like this one, all right? It's open section, so we assume that it's not connected. A little bit there, so that's fine, okay? Something like that, we hold it, okay? Now, at the end, you see in the hand here, right? So what happened? It's flat. Plain one. Plain one. Got it? Yes, very good. Now, Under torsion, when we twist, can you twist it? Yep, a little bit accelerated, but it's good. Tell me what happened at the end here. Yeah, so what is our? The tip here and the tip here, or the cross section, is go in and out in the longitudinal direction. Get it? So, it's interesting, isn't it? The longitudinal displacement is actually caused by twisting, torsion. Right? So now I'm not going to do anything in here. I don't touch it. It means that it's free. So when we twist it, it is easy, right? Can you do another one for me? If you hold that, make sure that you hold that. And make sure that the plan here is same. Can you twist it? How do you feel? It's harder to twist. Is that harder rather than that one? What that telling me? When you restrain that end from longitudinal displacement, or the other word or the other term we call is warping displacement, then you actually increase twisting capacity. Similarly to here, when you weld it or you touch or the end of the section, it's gonna help our column from increasing twisting capacity. All right? And that twisting is somehow related to the torsional capacity. All right? And that will affect your torsional buckling load depending on the condition of that end. Right? So, and now I will link that one into the LEZ and to explain to you what's going on. All right? So next one for LZ. So for LX, that's fine. Easy. Everyone say that's buckle this way, and then L is 1. LY is buckle in the wick axis, so it's actually moving this way. Right? You see the flange, and you can see the flange here, small flange. So it's just buckle this way. I make a cross section in the middle. It buckle this way, halfway line. Okay? So this, yep.
Previous slide, I have slight confusion with the LEX and
This one. Previous slide.
The orientation is something like.
Yep, the C section like this one.
Yeah.
And when you look from here, you see the flange.
So in that case, it is arresting in the X direction.
So x-axis is bending about
Out of
this one, our plane. This is our plane.
So that knocking is actually arresting that force displacement or what?
The knocking will help the LY. Buckle this one.
Oh, that way.
Yeah. So imagine this is the wall. I look it down. Okay. So this is your. You see here, and this is X, and this is Y. Okay. And if you look on this one you mean look this way, you see the flange. Okay, imagine you don't have the plastic ball, it will buckle in this way, it means that in X, in major axis. Yeah, everyone got it? And this one, Y axis, when it's going this way, it buckled in this way, and in wick axis. So the knocking actually reduced halfway length of that. Yes?
Regarding LEs, how come it is half? Because we are being restricted only at the ends.
Very good question. Then you actually read my mind. I've explained clearly in next slide. All right, that's good. Now, so in terms of X, everyone happy? in terms of why everyone happy. But you can see here that's twisting. When you push that one down, it twists. Looking now, it's just purely twisting moment, right? Torsional. And you can see the cross section twist. And the twisting now is 1/2 Y, right? In terms of the twisting displacement. So at the end here is 0. But when you go out of the section, it starts to twist straight away. So remember now, our twisting displacement along our length now, theta. Theta, how much is twist? So when you go out here, it just twists away in one side function. So you can see this look like a simply supported condition, right? So in this case, we assume that there's nothing welded or something acting on the end here, that we allow for warping. You see the tip here? The tip here go up, the tip here going down, so the cross section is actually jump up and down because of the twisting. So that jump up and down means that there's the warping displacement. Okay, another term for you to learn, okay? When we talk about displacement in torsion, and then one important term is warping displacement. Now everyone understand warping and how it affects, right? Back into your one, how it's gonna be. So now, you agree with me? LEZ in this one is equal to 1, because it's one side function. And now I will explain how it goes to half. Right, so in X, because we don't have knocking in our case, so LEX is equal to L and 1. But when you have L knocking, then you can see now our halfway, or our length now reduced to half. So that's why in equation you put 0.5 L, not L, right? Importantly, you can see in here, this one. When we welded the top chord or to the bottom chord, what I did is, I don't have the warping displacement in here. So it exactly like you fix something. So it means that right at the end in here, because you fix that one, it takes a little bit of time between it start to twist, right? And then twist in here. So our twisting displacement now is like this one. You go a little bit down here and then go down, and then back into here and go here. This one is still 90 degrees. Fixed end. All right? So in theory, like the column, it means that from here to here, we reduce to half. Now you got it? So everything we do now with elastic, we treat that as 0.5 LEZ. Okay? So now everyone got it? So I hope that, yes?
Do you have knocking here or no knocking?
Doesn't matter.
No, you have a restraint in the middle for this, for the last column.
For the twisting? Yeah. For the twisting is about twisting displacement.
It's the full length or you also have knocking?
Oh, you have knocking on that.
So the knocking does not.
The knocking not stopping from twisting. You know what? Because in general, the knocking just put one thing in the shear center, normally in the shear center, and this one, the section is twisting around the shear center. It doesn't go out and in, so knocking doesn't play any role here. Okay, you remember we isolated to pure mode. This is a pure twisting mode. Okay, so it's just twisting around the shear center. Okay.
What if there is knocking in two directions? Still it will be the same.
So if you have knocking in two directions, that guy will go up. It will affect LX. It will affect not affecting because it already has knocking. But the twisting, it doesn't affect because it doesn't stop you from the lateral or from the displacement, deflection displacement.
So for torsion, logging has no effect.
Yes. Yeah. Because it's purely torsion. Yeah. Yes.
Since in the earlier example, you have to put a tray at the top and
Yep.
to fix the.
To fix the warping. That.
So in that dimensions also plays a role in the restrainment, or simply fixity will enhance the complete restrainment at the end in the Z direction.
You mean
If the tray, the flanks are not so much high.
in the practice?
The example.
Example here.
Top and bottom, two trays to fix the.
Oh, sorry. Yeah, sorry. Yep. So in the
Top and bottom tray, flanges are not that much high to enhance, to enhance.
Yeah, yeah, yep.
Fixity.
yeah, so that really depends on the practical situation. So in this case, I make it idealize that to explain to you. To understand more about LEZ. But in practice, probably you need at least 20 mil or something. You're not going to touch it, right? So in that case, you can't fix the warping restraint. You have to design for free. Yeah, yeah. So L now is 1. Yeah, yeah.
I have one question. The knotting, are you attaching with the whip or are you also attaching the whip flange?
With knocking,
Yeah. So there is a
depend on the company what you do. All right, depend on how they want to do it. But normally, why here I don't have the detail here, but I understand they have to cut the slot or something they put in, and they have some particular detail on that. Yeah.
but the flanges are unaffected. Knocking is attaching only the whip.
Yeah. Oh yes, yes. You can do. I mean, this is just in general theory, on the stability. So it actually stop that from the movement, and that we can consider is simply support in here. You put a support in here, but it all depends on the detail of the company, or how they do it. Yeah. But it just affects the whole length buckling. Yes. Next slide.
So the first diagram shows it is rotated about the x-axis.
Yep. So this one is actually this way.
Then
It's IX. Okay? And this, you turn around, you see buckle in this way. Get it? This is where you cut in the middle. Okay. Yep.
when the logging is only one side, then
Yep.
can go to like double of
You mean
See, one notch, one direction notch only.
Mhm.
It's not opposite to it. In that case,
if it started to the left, then we can say that it goes to second. Then
I think in general, as long as you stop that whole section, that cross section from moving, that's fine. It doesn't matter you touch flange or you touch the web or something, doesn't matter. At that cross section, you stop that one from moving. That you can idealize the support condition at that.
Right.
Yeah.
In the regular practical, this type of strength will be used in the wall panels. So here the previous slides that we have shown, it is connected to the sheeting. Will the sheeting maybe avoid the different type of sheeting? Will it have any effect on that LEs there?
Yeah, so this one is step one. Yeah, so the reason I'm doing that because start from a practical application and then I tie with the ideal situation where we learn from theory. Of course, in the practice, it's more complicated, right? Because when you attach the plastic board, you have to take into account that and everything. You have to come into the bigger problem, and then you understand and design for that. And I remember Professor Madhavan did some tests, right? With the inclusion of the plastic board or something in your channel and bendings, and what is the effect. So that is the whole challenging problem as well. But it is just simply for you to understand the fundamental buckling of the member in different ways, in how lateral restraint stop and how warping and everything, so that you can understand. And later on, you can apply. Of course, there's some design guide for that for you.
provide some restraint for the channel.
Oh yes, that's totally different design.
Ignoring that.
Yep. So you need to go exactly to that detail, but that's not the purpose for this one. The purpose is just to bring it up. You understand the theory behind that and what is the LE, LX, and whatever in that equation. So that I want to bring in here to explain to you. Right. So everyone happy about that? I think this is the only way that I can explain to you. In terms of the observation. Otherwise, it's very hard to explain, particularly with the what we call is the twisting displacement. Everyone knows displacement like this one, and this one easy to understand. But twisting displacement, that is a little bit tricky. But now you can understand a little bit, right? When it's twist. Yes.
Since the logging is like this way, it's like, but when to bend this way, then logging also gives some restraint to the, like, since it is this way, it cannot, like, since its major axis in this way, so it cannot bend easily
Normally, if you buckle outside, it's not really helping. Yes, in terms of buckling, no, but maybe it's strength when you go ultimate. Yeah.
It is like, since the C channel, the logging channel is in this way, so when this, when the LDH, when they want to buckle about LDH, then that logging also gives some restraint to the thing because it cannot display.
I see what you mean. The rigidity of the of that one can affect, right? Yeah. So you cannot, then it's come to very complicated problem. Then you can do it. I think in the AS 4600 something allow you to design the purling with the effect of the raw bridging or something. If you're really interested, I recommend you to get this book from Professor Hancock. I'll show you. So he got all the example. Showing you design of the purling with the effect of the diaphragm or the effect of the roof sitting or whatever on that, and there's some model using the spring in. It's more complicated than that, but you can look it up. So really, if you're really interested, understand every from very fundamental theory to complicated or to applicate, you should buy this book if you really want to go into direct strain method. Oh, sorry, cold form steel structure. So I found this very interesting here. And the way Professor Hancock wrote that book, I like very much, is he keep it very simple. Very easy to follow, understand a lot of theory behind it, and you should get it. And then, okay. Now, keep going. This is warping. And this is, you see that? The red one, it just starts from here, not down here. So it's not twist until here and it twist. So this is 0.8. So now those effective lengths will affect your buckling load, right? So that one, when you got half, you put in here half, of course, Fy will go up a lot. Yes?
The last one, is it restrained torsion or restrained warping?
Which one? This one? The third one? The third one is restrained warping. It's everything about torsional. Okay, so that affects the L here, but LE here is actually LEZ, the length. That is the length subject to torsional buckling. That is depend on the twisting rotation, not about this one. Right, so this is flexural displacement, but this is torsional displacement.
Yeah, I'm asking whether it is torsion, rotation, or that warping. It's arresting actually the rotation, right? But warping.
Yeah, rotation. The warping affects the rotation. Yeah, right. The warping is similar to the column here. It's like column when you design the practice, right? If you have simply supported columns, yes, so it's buckled like this one. So K is 1, isn't it? And if you practice, if you welded the column like this one, it is buckled like this one. So this one, 0.5. It's exactly the same. but just instead of flexural displacement, is a twisting displacement, twisting rotation. Okay. All right, that's good. So yes.
I think, I don't know if I can be mistaken, but I think what he's asking is that there are two types of restraint.
Yeah.
One is a restraint for twisting, one is a restraint for warping. The twisting restraint is only to prevent the twisting in this direction. Warping is the movement in the launch.
So warping restraint is the boundary condition of torsion. Huh? When you put,
If it's simply supported.
yes,
Top is arrested, warping is free.
that's right.
So is it
It's simply supported, is warping is free. Okay.
here also we are flowing the same, or we are arresting warping also in this case? Here.
This one?
Yeah.
Yep.
So, you see, simply supported in terms of torsion, that means rotation is arrested, but warping is free.
Yep.
So, are we following the same here, or we are doing one?
We actually follow the same in here, but we just change the effective length. So it means that we treat the column from here to here simply supported. It's free warping in here. Right?
Free warping.
Yeah. No, add that here. So like a simply, like you separate that. Like you take that column and you got another little column in here, but with half. That's it. Okay? That's similar to the idea. So at the end, we still treat it as one simply supported, but it is shorter because of the restraint. That's it. That's the idea. So you can see that one on the bottom. So that one, when it's getting half, so it's actually increased a lot of buckling load or the torsional buckling load as well. Okay. So now we come back to our design. So we're going to design the column with those dimensions. And the effective length that we just calculate, Lx is 2000 and Ley and Lez is 1000. That's what we just got it from last couple of slides. Now what we do from thin wall 2, you run and you got 2 minimum point. The first minimum point at halfway length is 80 millimeter. Then you got lambda is 9. And then you can calculate the FOL. This is local buckling stress, the moment local buckling stress. Similarly, you get the distortional buckling stress is M is 245. So it's slightly bigger. At the halfway length is 600 meter. Okay, so the depth is 100. The halfway length is 600. So about 6 times of the depth. And the local buckling is 80. It's smaller, less than the depth. Yep. The depth is 100. So roughly that number, but it's not exactly the same. So local buckling. Right, so what next? So we pick up those stress, local buckling and distortional buckling. Then we got area from thin wall 2. And as mentioned before, because it's finite strip, so might be slightly smaller or bigger than the real one because of the overlap of the strip, but doesn't matter. We can ignore that. It's acceptable. You can use that, or you can use the actual area that you want from the manufacturer or something. And then you calculate the NOL, elastic buckling load. Very simple. Okay, you got buckling stress times with the full area. You got buckling load. This is 90 kilonewton for local buckling and 98 kilonewton roughly for distortional buckling. All right, so you got those two. First, now we calculate the member capacity of the beam. The column. All right. So we did it with already. We did with remember with the member capacity when we learned about effective width. We do that. So back into the previous one. Remember Fn we got to 13. Come back to that. And then we got NCE here. I is equal to 85 kilonewton. That is the member capacity. of the columns. And the mode here is flexural and torsional, it's combined. So then now we calculate the strength, local buckling strength of the column. And we take, firstly, we calculate the lambda, the slenderness, okay? And now we take NCE from here, and we divide it by NOL. That's we calculate from the single 2, and from that we can have lambda is 0.97. So from the standard, we compare with 0.776, we say that, all right, it's greater. So then we use that equation. So this is the strength equation for local buckling. Okay. Yep, any question? Good. And you can see that we're using NCE here. We don't use NY because we take into account the interaction between the global and the local buckling. Okay? Got it. So the strength now is 74.154. Right. So you can see just the first catch, that one, smaller than this one. So it means that it's going to fail in section capacity or combine or interacts between the local buckling and member capacity, right? All right, so we got a first strength, which is the local buckling strength. And now we move on to the distortional buckling capacity, or we can go as the distortional buckling strength. We're going to do exactly the same. We calculate lambda. And lambda here is equal to square root of NY on NOD. NOD is one for your second point. It's a second minimum point, right? From single 2. But what's different here is you're using U load in here. You don't use NCE. Because at the moment, we found that there's not much interaction between the flexural torsional of the member and distortional buckling. Because they are, for many reasons, we didn't see it in the test. So that's why at the moment, we calibrate just based on NY. Okay? And then we compare with that, and then we plug into our equation in here, and you can see that distortional buckling has the exponent here 0.6. And local buckling, you got exponent is 0.4. Okay, just something that you remember. And this is the strength, the distortional buckling strength of the column. And then what we do, very simple, right? We compare those three, and then you get that.
Sir, the previous distorting capacity that is the inverse.
Yeah, and what?
So the gross area T distress.
Which one?
NY, in distortion capacity.
In distortional buckling? For lambda, yeah?
NY.
NY, yeah?
That is A cross in TFY.
The cross area, yeah.
Cross area T yield distress.
Yes, yes. And remember in here, direct strength method, with all those one, we use full area. We don't have to worry effective with method. Everything effective is here, not. This one, this equation already take into account all that effect already. Right. So very simple, you don't have to worry all that effective with. Calculate what is the area of full section, plug into, and then you calculate NY. Okay? So you can see here, by using direct strength method, it's actually give you a little bit more load than you're using effective width. Right, so we have a bit of advance. It means that we have a bit of gain in the capacity. So it proven that is actually more accurate when we calibrate with the test. So so far, it's good for direct strength method. Okay, so let's go summary about the column, and then we have break. And then after that, we come back and do beam and shear. Okay. So just summary how to do it. First is from buckling stress. From thin 2, you get the minimum point, and then you got that you calculate the buckling load for local buckling and distortional buckling, and then after that you calculate the member capacity by using any traditional or conventional method. Then you plug into the distortional or local buckling equation, then you got another 2 strength. So at the end you got 3 strength, compare and get a 1. So in general, as we compare with what we learned last 3 days or something, you can see how simpler it is, right? Yep. So in here, probably 1 page, or you can get the strength. And the other effective width, probably, I don't know, depends on how we work, but maybe 5 pages, 10 pages. But the thing is, it's not that pages, but the simplicity. And importantly in here is the direct strength method cover the behavior behind that. We understand the buckling of the whole section, the local buckling of the whole section, distortional buckling of the whole section, and how it buckle, okay? We're not looking at the effective width and just divided element, and we just get confused. I don't know what's going on there, but it works. But we don't see the behavior behind it. Okay, so the heart of the direct strength method in here, you need 2 input. One is the behavior, buckling, and one is the yield, is material. The strength of the material, and then you mix that, and the direct strength method will give you. So what telling me here is still the semi-explicit equation. It's not 100%. We still have to do a curve fitting. This is actually curve fitting for the test. We just bring it down and up, calibrate the direct strength curve, but built in that we got the behavior. So we got the local buckling, we got the yield stress, and in the end it works. But it's still semi-explicit imperial equation. So we're getting there, and then I think at the end of the day, when we have enough power for a computer, everything, so it's everything probably going to the advanced analysis. Everything you build in finite element, and then you model, and it's fair whatever it is, and that is your design. So I think that's the future. But now, for member bias, I think it works. So that's it. Keep going. Yes?
In this expression, is it an interaction between the distortion buckling of the section with the section capacity?
This one, this is the with distortion or buckling, we don't have interaction. Is that your question? Yeah?
Because NY is impacted with the
Then why in here?
So section buckle capacity.
Oh yeah, yes, section. Yep.
With the distortion buckling, is it an interaction between distortion buckling to the full section capacity? This equation, whether it's exhibits.
So this equation give you, I don't know, I get your question right, but this equation use NY. So it means that full section, yeah, it doesn't affect by the member capacity. So it means that in N here, you're using that one in this one, but the equation itself is it's been calibrated already. It's been shipping up and probably shipping down because it's 0.6. Okay, you remember?
This is the interaction between the two. Interaction of full section capacity to distortion capacity, sir. This equation.
This equation is section capacity. Okay. It's distortional buckling. It's no
Interaction is
no interaction. It's just interaction between the mode, right? Either global mode or either local mode. Or either distortional, yeah. Not about section capacity. Section is different. So it's actually section capacity. It's NS. Yep. Yeah.
So, in order to calculate the global buckling, so can we use the same pinball program for calculating the elastic vertical stress and then find out the vertical stress,
You mean
FCRE?
NCD?
The next slide.
Next slide.
Yeah, that F1 is your calculated.
This one, yeah?
Global buckling stress.
And MN?
Yeah.
Yeah.
Here, we are actually getting the global buckling stress also.
Yes, yep.
Can we directly take that as critical buckling stress? From that, we can calculate the critical buckling load and substitute in ES equation.
No, but then you have to, okay, I get you what you mean. You need buckling stress, Fn. It's actually the one that we played yesterday, right? The buckling stress or Euler curve at the last one. But you need to put it into the strength curve.
Yeah, that is already there.
Yeah, so the strength curve in here. And A here, so remember still effective with
Instead of
method.
doing that effective with calculation, directly can we take that stress and substitute?
No, you need to calculate the strength of the flexure torsional buckling.
Yeah, that is there in DSM already.
That one?
Instead of taking F1 from the either plane, we can take directly from the halfway
We
plane.
can take it, this FCR.
In signature, there are global F1.
No, this is buckling. You mean the length of that, halfway length? You use that directly to here? What do you mean?
No. We can, so we are getting critical buckling stress corresponding to local and distortional from.
Yes, from the inverter, yeah.
Along with that, can we get the critical buckling stress corresponding to global as well from the signature curve?
That's right. So that's actually FOC. You don't need to work it out by FOY or the square root, whatever. That is actually FOC. But then you have to plug into the lambda, and then you got Fn, and from Fn you got the NCE. So that is different, yeah.
So that is what is prescribed by DSM. So the code which I understand is that way we are doing the calculation. For then taking the minimum. While taking the minimum, the first one is FOE. That means
FOC is a local buckling. Now, so this is Fn, is global buckling. F is actually, okay, let's get to the previous lecture. Is it lecture 3, is it? So where is FOC? Where is Fn you calculate? All right, so that is FOC. We got from last lecture, did you? Oh, FOC here is the one that you get directly from the halfway length from the thin wood tube.
yeah, that
Yeah.
we can directly take that.
Yeah. So we get that one. You don't have to worry about this one if you already have this thin wood tube. All right. And remember, I showed you yesterday. Depend on the length, and you can pick up this or pick up that. So it's actually the same. You can get that one. So this is elastic. Yeah.
Where should I get FOC? Exactly the available length, L or before that, to obtain FOC from the signature curve.
Yes.
Which location shall I take this FOC from the?
So the length, your exact length. So it's like 2 meter is 2 meter.
It's taken as full length. maybe the collapse may happen 90% of its strength.
That is the strength later on. But now we idealize that is simply supported. So that is full length, the side function. Got it? But remember, you asked very good question. So this is actually from thin wall 2, but it's buckling, not strength. Then you have to use the lambda, and then you have to use that to get to that one. That's right. Yeah. Yeah. Good. But you can save a lot of time. Just get directly from thin wall. It give you the whole member capacity.
So the only thing, once the length is very less, that it will fall in the distortional range. So we will find it.
That's right. So if we work from the right to the left, it's like an elastic buckling curve nicely. And then suddenly, because it's so thin, and it's dropped down because of distortional buckling, and then go up, and drop down another one because of the local buckling. Yeah. So it shows of the thin wall is all there.
So what if there is a bracing in the middle?
Yeah.
In that case also we will use the same FOC for the bracing because
if you have bracing in the middle, so it means that you cut into 2 columns. The column will be half. Yeah.
so that case like from which XCR we have to take it from the DSP.
For global or?
For global buckling.
Yeah.
XCR we have FOC as you said, we take it from the DSM. So if there is a bracing in the middle, then we like which FOC.
Oh, that is different, because it will affect your FOY, and it will affect the global buckling. Yeah. Then you have to do it. Yeah. It's not simple like you, because in twin wall they don't understand the bracing. They just assume that everything is just free. You just buckle in the easiest way they do.
Sir, it what? While buckling also will not be giving LEX, LEY separately.
In twin wall 2,
At last you,
yeah, because in twin wall 2 there's nothing to, there's no barrel condition here.
at last you are giving LEX, LEY, LEZ manually
Mhm.
the previous place. Then
Yep.
make it give this effect.
We can't use if you put a pricing in that, because you choose half of your member already. So LEY will be different.
Well,
But
analysis we can do. After analysis, there was a dialog box in that we are given FOA. There it is on LEX, LEY, LEZ in your slides.
in the program.
1.2.
Okay, so in twin wall 2, in twin wall, right? So actually, it's actually he do it for you. He program it, but he's using this equation, not from the halfway length from the thin wall.
So is discussion whether the section may go to the plastic states because
Oh, at the moment, so at the moment it's similar. Everything happened when it's buckle. It's not going to the plastic city or the compact section. Yeah, yes, you can design that. There's a rule in the DSM equation for that range, and you can design for that. So what I mean in here. Even now in Australian standard, you have the local buckling curve. It's not like what we do here. That is ideal, right? So this is 1. This is lambda somehow. So this is local buckling curve, strength curve, right? And from here to here, we assume that my is the maximum, so it's yield. But in the practice, it's actually from here to here. So that is called inelastic reserve range, and that allow you to design a little bit more more conservative, less conservative. It means that it's closer to the practice. So in here, there's the equation in the standard for design that range. Okay, but the way I teach in here is based on AIS and Australian standard from 2016. But just recently, 24, if you have a chance to download that, the direct strain equation is slightly different. Only one equation that is proposed by Dr. Klaus and Shepard. That what it means is they proposed the new one new equation that fit like this one. Right, and I think that's your question very good. All right, so no surprise if you go to the standard IISI, you see the type of equation. Can you write down the equation? Something like you got that? So then you will be not surprised that this is what we learned from FAM, and then what's going on in the ISI is totally different. It's not really 100%. They calibrate. They introduce the new format. This is the new format, but the basic is direct strain method. He will show you. For local buckling, right?
Yes.
Yeah, you can just, you can write down for everyone. Thank you for your help. A little bit bigger. So Pn, lambda. Okay. Yep, thank you for that. You see now that equation is actually the red one. It's tracking all the one that we want. So they're tracking that part. That is what we learned here, 0.4 exponent. And it's tracking this one is about inelastic reserve, the other set of equation as well. So to make it simpler, Klaus and Shepard proposed this one for every single curve. So in the latest one, 2024, you will find this equation instead of the equation that we learned, okay? But they are almost the same.
Only for flexion.
For everything, yeah. For column, beam, and even for shear, it's already done. And I think that is the future. So in the future, we develop all the new direction equation. We're gonna follow that format. Okay. Time for break, and then we come back and then we'll keep doing exciting work. Back to our lectures. All right, so the next one, I would like to walk you through the example how to design a simply supported channel section beam. And that problem is exactly the same that we've done. So we want to do it just to compare between those two methods. One is effective width and one is direct strain method. Same problem. We're looking at the C section beam. It's a purlin or roofing system, and that's subjected to uplift loading. Uniformly distributed uplift loading, and the length is 7 meters. And you have one row of bridging in the middle, and then we can see here. So this is uplift, and one row of bridging in the middle, and this is the cross section that we wanted to design. So this is very typical section for purlin in Australia, 200 millimeter depth, 1.5 millimeter thickness, and the flange is 75 millimeter width. And we're using G450 steel grade, FY is 450 megapascal. Oh, right, that is, first is we calculate the member capacity. Right, so that is based on the standard And as you imagine here, this is simply supported, subjected to uniformly distributed load, so you will know that the bending moment will be like this. And remember, because of that, we need to work it out the CB factor to take into account the shape of the bending moment. And that's why you got M max, M5 for 3, plug into this equation, you got CB factor. And from CB factor, you put in here, and then you can calculate L01 and other MOY and LZ2. Then from that equation, then you can calculate M naught. That is the elastic buckling moment of L. Right, so similarly to the column, the rod of bridging will play a role in the buckling load, right? You remember? So it's going to reduce L effective somehow. So you can see when you put in here, the cross section is like this. So I can draw a beam, see beam here. Sorry. So if you restrain, for example, you put a support in here somehow. So you can see this is X. So this is a little bit here. This is y-axis, okay? So when you bend outside of the plane here, which is bend about out of our plane, right? So it's in weak axis somehow. So in here you can see our equation. There's two terms here that has the meaning behind that, right? So this is the F of Y. So that is buckle outside. So it means that when you have this one, like exactly like knocking in column, then it's actually reduce your L-O-Y. But L-O-Z is not right because it's twisting. It doesn't matter. That one is, you can twist in here easily. So L-O-Z, I think, is going to be Z. So if we cut a cross section right in the middle, it's going to buckle like this one. If we don't have that raw bridging, it's going to be like that one. Okay? So what happened is our section will go out a little bit as a UB. So that is lateral restraint, and then it twists about one angle is 5 theta, so it rotates. Remember, it's rotate here, it's rotate about shear center. Okay, important. So if it's this one, it means that it buckles sideways and twists. So that sideways, that will represent. And the twisting here, that MFOZ here will represent. So everything that here represents the behavior is actually in our equation. Right, so this is buckling, where we assume that is uniform bending. Then we factor that with CB because the shape of the bending is like this one. I just like gradually walk you through the meaning of every term in the equation. Right, so now the beauty of ThinkWork is let ThinkWork working hard for us. We can have coffee or doing something else and click a button, and here it gives you everything. IX, IY, RY, RO1, and importantly is IW. It's hard to calculate. then it gives you, that's warping constant. And G, torsional constant, J, shear, J, and then Z is effective section modulus. Sorry, not effective, section modulus. Right, so that one, you can see now, we plug into that equation. Right, and Ly here is actually related to what I just talked about. Then you got 114 megapascal. That's FOY. Do similarly with FOZ, you got all what you want. You plug into those equations, you got 97. So that is FOZ. And from that, from the equation, from the standard, you can calculate M naught. Yes?
In this beam is what will be the effective limit about Z0? It's the same as delta or something?
You mean in this one? Yeah, because you don't have anything to restrain that from warping. So it means that it's free. So this is the whole length. Yeah. Unless you have to weld it in here, a very thick plate in at the end, then it's stopped from warping. Then LEZ might reduce, okay, to half.
So that will be more happens over the truss.
Yeah.
The sheet is not discontinuous, that is the overlap. Some point it is continuous also. In that case,
That will be more complicated. Then we need to look at one particular case. We look at that. Yeah. But in this case, just in the general, we can use it. But when you break down into, so that's why engineers, important to make decision what you're going to do, what you're going to design. Okay, but back into those one. This is in theory. In theory. However, in the practice, even in the standard code, you remember the columns in hot rolled steel, right? So this is a column beam. When you put the load in here, T, so L here is 1. Everyone happy, right? The L effective. But if you put that one, fix in, so L now, 0.5 is in theory. But in standard, is actually 0.7. So it's more conservative. So what standard saying, no matter how good you put effort to make it fixed, but it's not really fixed. So that's why they put it up a little bit, just to make sure that you cover that uncertainty. So that's how it works, okay? But in theory, of course, it's 0.5. Right, so then we calculate yield moment. And very simple, you got the you got the section modulus, you time with yield stress, you got a MY. Very simple. You got buckling, and you got yield here. So what you do next? From the thing with 2, you have 2 minimum point. One is local buckling, and one is distortional buckling. Remember, this is the stress. And then what next? We calculate the elastic buckling moment, elastic local buckling, MOL. Just take the stress time with section modulus. Sorry, yes. Then you got, this is MOL. It's the MOD. Very, very, very easy, very simple. Then from that, you need to calculate the member capacity of the beam. And that is not direct strain method. This is not new, this is old. So you can see here, depending on the slenderness of the beam. So what I mean here, the slenderness is depending on the number of branching, the number of the rod in here. If you have enough bracing, then you calculate ME, MBE, because you can imagine that you have more of raw bridging. It means that your effective very much smaller, right? And when that one's smaller, it means that M naught in here is going up very fast. So it doesn't buckle. So then what you focus the member is going to be here. It's getting yield. You maximize the section, the yield. Okay? And then somewhere in the middle range has a little bit of inelastic buckling. And then back into your question is about the imperfection and residual stress or whatever. And that range will cover. Okay? Somewhere between the yield and the elastic buckling. So it means that you have a decent number, but not enough. Now, if M naught is a lot smaller than My, in that case, it means that in the signature curve, you right at the end in here, so you don't have anything to stop from flexure torsional buckling, then it's purely elastic, M naught. So that is the meaning of every equation in here. Depend on the slenderness, and that slenderness is depend on how much you provide lateral restraint. Okay. So back into our problem, we got M naught 7.361, and it's smaller than 0.656. So we actually in that criteria, and that's equation. All right, and then you can calculate that M naught. So from the first equation, we know that our member capacity now is equivalent to elastic buckling. All right, so and then next step, we move to the section capacity. All right, so the first minimum point, local buckling. We got already MOL, we calculate from thin wall. MBE, we just calculate on last slide. And we plug into that equation, we got the strength, MOL. That's the local buckling strength of the beam. And remember, in here, you see that we use MBE, not MY. So in the other word, we're gonna take into account the same, like the interaction between flexure torsional buckling and local buckling. Okay. Now we plug that, we calculate lambda is the slenderness, and then we compare with the 0.776 for local buckling. Then you get that local buckling equation. You got that is MBL, local buckling strength. Okay. And similarly, we move to distortional buckling strength. Same, we got MOD from signature curve. And now you can see, because we don't take into account the interaction, we use MBD is MY. And from that interaction, from that DSM equation, we can calculate the distortional buckling moment, the strength, okay? So 9.593. And what is? At the end, we just compare of three of them, and then we choose the smallest one is 6.964. And we time with load factor, 0.9 for bending, and it is the actual ultimate capacity of our beam in that case. Okay. And then we can back calculate the uniformly distributed. It is 1 kilonewton per meter. That is the, so then we compare with the load that we apply. Now, move to my baby, shear. Right. We're gonna design that beam, not design. In shear, normally you design for bending, right, first, and then we check for shear or combine bending and shear. That's what you do. No, you don't design shear straight away first. And what we do now, you can see one of the photo from my test, long time ago, no, my student test, and you can see next to the support, you might see the failure in shear, 45 degrees, and it's happened mainly in the web. So this is critical if we don't check and make sure that sometimes the bending is good, but then it might fail in shear. Right, so the cross section is same. We use that, and then from thin wood 2, give you that one. And come back to your question, a very interesting question. With shear, we don't have second distortional minimum point. Okay, we just have the local buckling because of shear. All right, so interesting for shear, you just check for that. You don't need to worry about the distortional or other things. We just got that minimum point, and you plug into, and then you time with load factor, then you got the shear buckling load V critical, and then from that you calculate the Vy, the yield similar to My, so you calculate the Vy, and in here, very popular equation in standard 0.6 of D1, you just take into account the flat web portion, and then you time with T is thickness, Fy, you got a Vy. And from that, you got the direct strength curve for shear, and also depending on the slenderness. Then you can calculate the lambda similarly, and then you get to the end in here. Okay, so that's how, yes?
The earlier shear capacity, shear yield load capacity. But we're holding.
Yeah, this one, is it?
So this is FYP root 3, isn't it, sir?
This one?
Yield stress. There is a
Yield stress?
area
Yes, shear area, yep.
divided by root 3.
No, we use straight away Fy.
No, this point
That is
0.58.
Yeah.
We rounded up to 0.6.
Okay, so interesting here. It actually square root of 3 on 3, yeah. Yeah. So this is 0.6 from Australia, but in AISI 0.64. Okay. Yep. So we round up a little bit. So this is Australian standard. We use 0.6, but when you look up the IISI, 0.64. 4, right? 57, right?
ASA 64, Indian code 54.
Yeah. In American, 0.64. Yeah. But in Australian, we use 0.6. Yeah. But it actually built in that is a square root of 3 on 2, I think. Yeah. Very good. But Fy here, we're still using the yield stress for normal stress. Yes?
Rather than when we use the analytical expression that K5 square equal to 21 minus Q square for calculating the shear buckling stress.
Shear buckling one?
Shear buckling
Yes,
stress,
yes.
the analytical expression.
Okay, so you can use that one, but on your question, we have that fundamental Timoshenko equation, right? Kv is equal to 5.34 plus good 9 point something. And when you take into account the web panel, and at the appendix in AS 4600, we have an equation to take into account the flange as well. Yeah, so in equation there's something about KSS and KSF where it's take into account the rigidity of the flange into. So you can actually get it in the other way, analytical one. Yes. So instead of using thin wall, you can use that equation straight away. But at the back, not in the main, because in the main is still fundamental Timoshenko equation, 5.34. Yeah?
There is no partial set factor for stress here.
The stress? Stress in here, we bypass that one by go straight to load. So you got a load factor to time with what you got in the minimum point, the load factor, and you time with the load that you apply at the beginning, and you got the buckling load. Buckling stress, you found very good question. It's a little bit tricky with shear. I tell you why. You can work it out the stress, and you time using the KV, that's Timoshenko. The problem with that, we need to bypass that. Okay, I should in that one. And I think we have to use the load factor. It's more accurate to get straight to buckling load. Because if you're working the stress from shear is a bit tricky. Because the stress distribution is like this one. You got here and you got a parabol here. You got, and there's your lip. Right. And that caused because of the shear flow. Okay, and it's going up. So the maximum shear stress actually in the middle here. But when you calculate this one, you base on the web only. So normally if you calculate the stress, you have to take into account the average somehow in here. It's not a maximum one. So a little bit tricky. And then you remember in the equation for shear, you calculate that you have D1 on T, and that you didn't take into account the flange. So when you can work it out the eigenvalue here, and you work out the stress, and you back calculate the load by equation KV, right? Something and related to. So then, as I explained, you're using average stress, and you're using that area only. Because you divide it by stress, right? Shear stress is load divided by area of the web, not everything. So a little bit of tricky, not much different here, and then even a little bit more complicated if you want to take into account this a bit of area here as well. It's actually the other way around. It's go up the shear flow. So if you take into account the stress, it's a little bit more complicated. But if you calculate straight away from load, that's just you bypass that. You get buckling load straight away from eigenvalue. Right? You run analysis, you got a load factor, time with whatever load you put in, that is very critical. How simple is that? Okay? It's good. So this is the equation, of course, and then we check. We got a shear, and then we calculate the shear as the support, and you calculate the shear design, okay? And then you can compare with the bending moment that we have, and you can see that the shear capacity is okay. It's smaller than, it's bigger than what you expect, so it can carry good, okay? So this is how simple it is. When you calculate that one. But of course now one will ask question, okay, is that the section normally close to the support, and you need to cut a hole to feed all the MP or plumbing or electricity or whatever, then you need to calculate, and now it's already in AS4600. You can design or using DSM for section with hole. So something for you if you're interested, and you can learn a little bit more, okay? But within this series of lectures, I would like to give you a big picture, very fundamental, explain to you how DSM works, and then if you want more detail, of course you can look up in the standard. There's a lot more than here, but it's still on developing. We still keep updating. And hopefully in the future, I talked to Professor Madhavan yesterday, we might take into account all the new of his research and the team, and we might bring it in the standard, hopefully in the future. So we can discuss about how the possibility of that. So it means that it's going to be exciting later on in terms of the development of the DSM or in the standard. So with that, I think I just finished now, but not conclude. All right, just finished my presentation, my lectures. But now we're open for any question, and we can discuss. Yes.
So, what is the criteria as per Australian standards for considering high shear? That means interaction between bending and shear.
That's really good question. At the moment, the shear is a very tricky problem, as you can imagine. Shear is a product of moment gradient. We don't have such a shear situation in the practice, right? No matter what you design at the shear one, you got a bit of bending in that one. So at the moment, we isolate it and treat it as a pure shear or predominantly shear, and we assume that there's no bending to come in. However, when you move a little bit out of the support, then you got more bending coming in, and that is very important for interaction. So we already, one of my PhD students, Dr. Pham, another Pham, so he did a lot of work on the interaction between the local buckling and the bending, and we're very fortunate that we have Professor Madhavan is one of his examiners, so here he will explain, he will know exactly what's going on in that space. But we're working on that. But at the moment, what he proposed now is just the interaction between local buckling and the shear. We haven't got to distortional buckling and the shear, because as I mentioned before, with the distortional buckling, you need a longer halfway length, right? You got a 6 times of the depth or something, and then when you get something more than 3 times of the depth, then the bending will come in straight away. Then the interaction is meaningless now. So I think it just works for local buckling when you consider a very short span, and the interaction maybe up to 2.5 at the moment. When we test in the lab, we can see the interaction or shear. But other than that, up to 3, then bending just come in straight away. Particularly for thin wall section, not like hot roll, right? Hot roll you can go up to 3 because of the tension field action, and the flange is good enough to hold that, so it creates a large tension. But the cold form steel, because the nature of one section, one thickness, is going to fail in local buckling, unfortunately. So that is how we're doing. So very good question on that. I mean that you got it very deeply, but that's what we do. But in the other area we just finished, and hopefully we'll bring into our standard, is the combined action between shear and compression. Okay, so you might ask me, what case that you're looking at? Why is you looking at the compression and shear? So imagine like in your high-rise building, you got this is the beam, you got this column, right? So the beam at this area is shear, a lot of shear. But when you design, when you got a high-rise building with high load, wind load blow in here, so that one actually pushing to our member, and that member go into shear core. So these are actually a huge compression as well. So then we need to look at the interaction here to see what is the effect of a combined action, compression, and the shear. Okay.
So in that case, bending also will come in.
Yes, that's right. Yep. In some case, when you have, for example, you got a column sitting on the beam, and somehow because of the architecture, you're not happy, he want to move that column a little bit in, so that is really big shear on that one. So that case you need to consider shear in that high zone shear. Okay, and that causes another interesting problem as well, because you remember bending and shear, they all happen at the same time because it's products of bending. But compression and shear is not always same, right? Because shear is always there, because the load, when you apply gravity load, everything, shear is there. And then later on, the wind will come, and then we'll apply the compression. But that is for building. But the other way, like portal frame, the compression is not important yet for the column, right? But you got a wind or something in there, so wind maybe come in first, and then suddenly snow come or whatever, and then the compression big compression come in later on. So the sequence of loading is important as well, and how it's effect of interaction. So that is all thing that we need to think about that, and then we put in the in the research. We did already the test with different sequence and how it works. And then hopefully we can come up with some nice equation or proposal that we can use later. Good question. Just something to share with you. If anyone want to ask question, I'm happy. Yeah.
One fundamental question, sir.
Yeah.
In hot roll steel design, we will limit the design stress by some factor. But in cold form, we are taking the indices as it is. Because of the post-buckling strength, is that the
You mean you limit? Maybe I haven't got your.
unit state approach, we will limit the stress into design stress
Oh.
using some partial safety factor for yielding.
For yielding. Okay.
So we'll take the FY by gamma m naught.
Right.
Reducing the stress by some 10%. So 90% of the yield is to be taken for the design.
Okay.
But in cold form, we are directly taking the FY as it is.
Okay.
There is no
Yeah, it's no reduction now for yield
because of
strength.
the post-buckling strength is there.
I think that part of the reason post buckling or maybe buckling coming in, stability coming in, so yield stress just there. But the other, I'm not 100% sure how it works, but at the moment, based on what we got in the standard, we don't have any deduction that for the yielding.
Maybe I can answer that.
Yeah.
So, codes are partly rational, partly emotional. So it's not a 100% scientific document. It's a collage of several people putting together evidence. So even in IS 801, the latest revision, will have the same safety factors that we are talking about approach to, that we'll have for 1.7. We'll have
In our Indian standard.
in Indian standard. Even today, if you look at British standards, Euro code, or approach they use 1.0. They not use 1.1. That means that they have trust in their manufacturers.
Depends on the manufacturing of it.
So manufacture of the material, also the quality control is being done. So they have any product sourced in Europe, for example, making better quality. So that trust actually is reflected in the code as 1.0. The same trust is there in Australia because Blue Scope is manufacturing. They have that they will get what they want. But in Indian standards, perhaps that may not be possible because we are really worried whether they produce that or not. And let me complete. Right? The best way to respect someone is to wait for someone to complete and then we are. So we don't have trust in our product, so we actually don't want it to be reflected because of safety concerns. So then we put it as 1.1, and that's what we do. And perhaps the same thing is reflected if you look at the code for connections. For connections will be typically 1.25 partial safety factors. For bolted, when it comes to welded, it is 1.5 and 1.25, 1.25 for shop, 1.5. That is also because you are doing welding work here, where gravity will not support you, so instead the weld material going inside, the other material will go. If you are building it like this, the weld will deposit, the other garbage will be deposited on top, so that is the reason. So it's nothing to do with hot rod or cold form. In my opinion, I think that is because of our product. Other companies will not do that.
Yep.
You told in Europe they put one. That's why in the working curve they will have the DA star.
No, the A star is actually not necessary for the material. Safety factor is something you do 100% everything right. On top of it, something you did not anticipate, that is why you have safety factor. It is like saving money for your daughter's wedding. You don't take it out every day from the State Bank of India. You put it, done. When she comes to 18 years old, you take the money. So the safety factor is also like that. You don't take that. This A star that you are talking about is the quality of the fabrication in terms of two things. There are two residual stresses that can happen, imperfections that can happen. One is the out of plane. Right? Another is the manufacturing process. Out of plane is when you produce a structure, it should not have curvature curves, right? So there are several things: twist, bow, camber, flare, bore, bend. So there are 6 different types of imperfection. All imperfections should be very correct. So if you are producing a very ideal cross section, close to ideal, that is one. Another is your manufacturing methods where you have thermomechanical processing where you can control your residual stress to 8%. So that is a trade secret. JSPL or JSW or Tata will not tell how they are producing it. So that's why you heat it, cool it, you do something, and so that the residual stress that is locked in will be 8%. But such residual stresses you will not get it when you cut a plate and build it. Where you don't do post, reduction in thermal stresses, that you get what it is, right? So those two things, one is out of plane, another is your controlling of residual stresses. If it is very well done, right? They say that you are very superstar, 24 karat gold. That is what they call this A0. We are not able to achieve that so far for the last 15-20 years, so we start ABCD. Apparently in the latest bulletin they are saying that we will come up with A0 as well, and it has been included. So that has nothing to do with safety.
In the case of cold form, there is a post-buckling strength.
Yes.
So our Indian standard code allowing reduction also. Already there is a reserve strength for.
So you adjust the curve. Yep. Similar to your strength, we got a factor.
Specify some factor.
Yeah.
So we are considering doing the design because of you are not having the section as per the ideal condition.
And can you repeat the question again?
So actually in the cold form, in cardboard it is okay because of
Right.
the fabrication. But in the cold form, after reaching FA there is no failure, it is going to the next stage post-buckling strength. But in our code, we are also introducing a reduction in the FO itself. So what
In
we
the hot
do,
room.
cold form I'm talking
Okay.
about.
Which code are you saying? We don't have.
8.1.
8.1 1975. Because 8.1 latest one has not come out.
Yeah, 8.10 certificate.
1975 they do post-buckling and hard covering.
They are not using post-buckling strength explicitly.
Because there was no knowledge of post-buckling strength in 1975. Research was still conducted at Cardiff University of Manchester, they are not understood. They know something is greater, but they was not able to quantify it. In fact, bulk of the work started from the failure of the bridge in Manchester that led to the development of post-buckling. So that's why you have the Cardiff model and everything. It's like faster model, Cardiff model. That is actually the work carried out from 1970s to 80s. It would be hard for me to believe that Indians actually were able to understand post-buckling in 1975 and introduce it.
But in the new code,
It has no reduction. In new code it is included, but post still again you cannot take it as a birthright as post-buckling will be there. Post-buckling also depends upon your boundary conditions. If you have a proper boundary conditions, you have most post-buckling. If you don't have proper boundary conditions, if three sides are simply supported, one side is free, the amount of post-buckling reserve capacity that you get is peanuts. It is basically not all that. But if you have four sided simply supported or four sided fixed, then you may take advantage of that. So simply because a plate is thin, doesn't mean that you are post-buckling. Right? You should have so many conditions to establish post-buckling in order to take advantage.
Very thorough question. Thanks. Yep.
So, if there are no questions, can we break for lunch and then come back? Good, thank you.
Right. Thank you for today.